Now, I'd just like to give you a brief introduction to the project, if I may. The Energy Pathfinder project is a project funded by the Northern Periphery and Arctic program, and it is aimed at addressing priority number 3 of the program, which is the fostering of secure communities through the provision of renewable energy and energy retrofitting. It's really speaking, we're not looking at energy retrofitting, we're looking at energy management here. Sorry, I'm going to try to get that screen share again. Okay. The project had a short preparatory project, which began in 2018, lasted 6 months. It actually put the project together with the full consortium. And the full consortium you can actually see in the slide there. If I can get these pictures out of the way. It's led by UCC, and partners are NC Installation, the University of Umeå, Landsverk. Sorry, don't go yet. Can we go back to the Landsverk, the National Trust, Land Trust for Faroe Islands, Historic Environment Scotland, and the Oulu University of Applied Science. So it was a partnership of 6 partners in 5 regions, and the project is called Approaching Near Zero Energy in Historic Buildings. It was approved in 2019. It was originally supposed to run for 36 months, but it was extended by a further 6 months due to delays resulting from COVID, and now will be completed in September 2022. Next slide, please. The Energy Pathfinder project is looking at a number of case studies of historic buildings and looking at approaches to retrofitting, to integrating renewable energy, and also to monitoring energy use and improving energy behavior in 6 buildings. 2 of those are in Cork. One is my Rosswood House in West Cork, which is currently managed by Green Skibbereen. UCC was responsible for working with this demonstrator. And another one was Cork Cathedral in North Cork. And the main purpose of the project there was to look at energy performance and energy monitoring. And that's the purpose of this seminar, to look at the work that's been done in that under the guidance of NCE Installation. Next slide. Energy Pathfinder had a number of objectives, as I alluded to earlier. One was looking at potential retrofitting of historic buildings. The other one at renewable energy integration into historic buildings. And then appropriate energy management and monitoring. And this is really objective number 3 is what we're looking at today, and an example of how that has been implemented. The project also considered integrated environmental management, as you see in my Rosswood, and innovative and inclusive social uses, which most of the demonstrators have, including Cork Cathedral. And also, finally, at replicable financial models and roadmaps for other owners and users that want to improve the use of historic buildings. Also, the project has developed an online toolkit to help owners and users decide what measures to take in their buildings. And this can be found at this website address here, eptoolkit.eu. Next slide. In terms of energy management and monitoring systems, you'll get a fuller explanation at this session, but we're looking at systems that were cost-effective and replicable, that facilitated participation by building managers and residents, that enabled improved energy behavior, that contributed to improved energy behavior, and that also could be demonstrated to gain significant reductions in energy use. And this is what we'll be looking at this afternoon. Next slide, please. Barry. Next slide. Finally, if you want to find out any more about the project, this is our website. You're probably familiar with it already. I'll mention the toolkit, and the toolkit may be found at that address. I'm Jose Ospina, project manager, and you can find me at this email address and phone numbers. And now I'd like to hand over to NC Insulation and to Barry for the presentation. Thank you very much all for attending.
Perfect. So over to me, I guess. Thanks, Jose. Thanks, William. I'm going to share my screen there a second. Should be allowed to do this. Thanks, everyone, for joining us today. Let me know. You can see that now, full screen on everyone's screen?
Yes.
I can't see you guys anymore. Perfect. Thanks, Jose. So, hi, everyone. My name is, you've got it. Hi everyone, I'm Barry Bambury. I'm Operations Manager here at DCSix Technologies, and today I'll just be walking you through a piece of heating analysis we did at the North Cathedral in Cork. So the building itself is over 200 years old, but recently there's been a number of energy efficiency upgrades that have been carried out. So there has been LED lighting installed, solar PV, 5 kVA of solar installed on the roof of the building. There's EV chargers installed outside for anyone that wants to bring in their EV and wants to charge it up. But what we'll be looking at today is the space heating on site. So there's been an air source heat pump that has been installed, air-to-air system, but there's also the older gas fan heater that's still installed in the church. And what we'll be looking at today is kind of how we're advising the church on when or which of these two technologies should they be using and when should they be using them. Because I suppose when they first came to us, there was a lot of uncertainty about which device is more expensive, which was cheaper, and I suppose what time of year one might be better than the other. So what we did was we installed energy and environmental monitoring. When I say environmental monitoring, we were looking at temperature and humidity inside the main part of the cathedral, and we left this equipment there for about 3 months, and then we looked at how we could use the data that we gathered from these devices and come up with like an operational spec for the people that manage the building that would be simple and straightforward for them to use, and they could make kind of easy decisions off the back of this and hopefully have a dramatic reduction in their annual heating bill. So just to kind of set the scene, I got sent on this cool video, some drone shots of the church just to set it for you. I'll try and play it now. I know it always comes over a bit glitchy on your screen, but hopefully it's somewhat clear. So this is the building at the church. It's over 200 years old, top of Shandon Street there in North Cork. You'll see the solar PV there installed on the south side of the building, 5 kVA, installing or producing over 4,000 kilowatt hours of energy a year. So impressive stuff. And then previous to this, there was LED lighting upgrades. So I was saying there about 80,000 kilowatt hours has been saved from that LED lighting upgrade. So that's a phenomenal amount of energy. I think it equates to almost 20,000 euros at their current energy tariff. So the church has already made some very big improvements, but one of the areas they've been struggling, I suppose, is with the space heating, and that's what we'll be going through in the rest of the slides. So as I say, air source heat pump installed outside the building. There's the EV charger as well, air-to-air system. So this blows warm air over the church and into the patrons that are using it inside there. And then we have the gas heater. So the gas heater was left in place even after the air source heat pump was installed. This gas heater is an enormous piece of kit. You'll see it there on the roof. Huge piece of kit, 300 kilowatt product consumption. And on top of that as well, there's a 3-phase electrical motor inside there to just blow the hot air out. And that produces 10.5 kilowatts of energy. So this is a huge piece of plant, very, very effective at heating up the church, but obviously less environmentally friendly because it consumes gas. And yeah, we'll be just looking at how these two different pieces of technology perform. I suppose before we get onto that, it's worth looking at the space. And I know you're looking at retrofit a lot with this project. So it's always kind of a fabric first approach typically to retrofit in Ireland. Very unique space you're dealing with here with the church. Few things to consider. One is kind of occupancy hours, or hours of the day that this space needs to be heated. Typically, you're talking about 1 hour per day, so very, very small. Normally, when you're looking at heat pump solutions, you're looking at a lot, heat pump to be operating throughout the course of the day. Here, we're only looking at actually heating the space for 1 hour. On top of that, we have the fabric of the building. You have these beautiful stained glass windows, obviously single pane, very large as well, even for a church. A lot of churches in Ireland are much darker. This is a beautiful, bright church, but because the area of those windows is much larger, again, fabric heat loss is going to be very significant out of those windows. Then finally, you have the amount of air you're actually trying to heat up within the space. You have this huge, beautiful suspended or arched ceiling. Again, here, warm air in the church is tending upwards, and just a challenging space. Couple that then with the fact that often case the people using the church might be a little bit older. The church has to be a comfortable place for them to come into and to use. So I suppose the result at the moment of all these different factors is the overall energy bill is very substantial here, particularly for space heating. So that kind of sets the scene of how challenging an environment this is. So I kind of waffled on there for a little bit, just to kind of give you a kind of overview of the goal here, just to kind of summarize it in a sentence, is to optimize the operation of the existing heating infrastructure. So use what we have, optimize it, and our goal is minimize energy spend while maintaining comfortable temperature within the cathedral. So maintaining temperature, can't change anything about what we have, can't upgrade, maximize what we have at the moment. That's the goal, that's what we're working with. I suppose existing heating infrastructure, I've talked about the air source heat pump, I've talked about that big gas heater on the roof. There's also a more traditional gas boiler that heats the back offices inside in the church and some of the bathrooms and stuff there as well. So that's part of it. So the kind of the measurement that was there before we came along was the two bills, the monthly bills. So the gas heater, that comprised of the gas heater on the roof and that gas boiler that heats the back offices. And then they had the monthly electricity bill. So that electricity bill contained the air source heat pump consumption. Actually, the fan as well is a big consumer for them that blows out air from that gas heater, and as well as everything else in the church that uses energy. So you have the lights, EV chargers, and everything else. There's a back kitchen there as well. So a lot going on, and the church with their current energy bills coming in, it wasn't apparent to them, what was actually, where was this money, or where was their money going every month, what devices were consuming the most. And so that's where we came in to give them a hand with. So what we did was we installed environmental and energy monitoring. The environmental monitors were wireless sensors, a pair of wireless sensors we deployed within the main cathedral. They send back information on temperature and relative humidity. But also what we sent back was, or installed, was some of our Watrix energy monitoring devices, these devices here. And what I'll do is I'll just skip forward a slide and explain how the Watrix device works for a second. So Watrix, I'm sure some of you are working on this stuff all the time. You might be familiar with similar technologies. This is a piece of technology we developed in-house at DCSix. It's a 14-channel CT energy monitor. For anyone that's not familiar with how this works, this device has 14 inputs along the side of it. You can input a sensor called a CT or a current transformer. Current transformer clamps around a cable that might be going to a piece of electrical equipment within your site. So it can be a short heat pump, could be a lighting circuit, could be an oven, it could be absolutely anything. And it wirelessly monitors the amount of current flowing to that circuit. So we monitor the current here. We also sample the voltage on site via 3-pin plug. We just have a little sensor that plugs in here, that plugs into the wall, just like your phone charger or laptop charger. That tells us the voltage. We sample both. That gives us, we're able to work out the kilowatt hours. We're also able to work out reactive power and stuff like that. But what we're really interested in here is kilowatt hour consumption of the various circuits inside in your site. So all this information is, I suppose, first of all, it's stored locally in the device, but then it's sent back through a secure VPN network up to cloud and into a dashboard like the one you can see here. So that's where all our data is accessible to both myself or any one of our customers, in this instance, the people that run the church and the guys in NCE. So that's how it works. I'll just kind of skip back again for a second. So what we actually did here inside the church, we actually installed 2 of these devices inside the main electrical panel. We had the 2 temperature and humidity sensors. For this project, we didn't actually install gas monitoring. We didn't directly install gas monitoring, should I say. What we did was we put CT clamps onto, I suppose in the case of the gas heater on the roof, we put a CT clamp on the fan motor. So then we were able to tell when the fan, when that gas heater was turned on or when it was switched off. So that gave us an idea of the operating hours every day, or time series operating hours of that piece of plant. What we also did was we were able to put a CT clamp on the circulating pump for the boiler that heats the back offices. So, and we were able to look at the nameplate on both that roof-mounted gas heater and the traditional one that heats the back office. And from the two of them, we were able to make an estimate of, okay, looking at how often they're operating, how many kilowatt hours do you expect these two pieces of plant to use every month? And then we were able to cross-check it with the monthly gas bill to make sure we were within 90%, and we were going to be able to make educated decisions off the source of monitoring we did. So we were able to get in within 90% of the correct answer without actually installing any gas monitoring. So that's kind of the practical side of energy monitoring when you don't have an infinite budget and you have to, make smart real world decisions. So that's one of the decisions we made on this. So once we were up and running, we had minute by minute consumption on the air source heat pumps. We're monitoring power to the air source heat pumps. Environmental, again, minute by minute data coming back from those sensors out remotely in the church. We had kind of estimated consumption in the gas boiler minute by minute again here, because we could see when that pump was in use, and the same thing again for the gas heater. So that's kind of, suddenly we had all these data inputs feeding back to us. What we did was we left the system in place. We installed it just before Christmas, left it in place, and we monitored, I believe it was from the 1st of January right up until the end of March. So we had a good portion of their heating period. And then we said, right, how are these two pieces of plant performing? So the first, when you're looking at a piece of plant that's heating a space, the first thing we looked at was the actual heat output. So the ability of this piece of equipment to heat the space. So we found out the gas source heat pump, we discovered that the fan consumed 10.5 kilowatts of electricity when in use. And when in use, it also consumed 289 kilowatts of gas, assuming 85% efficiency, and you get the two of them together. We have total combined consumption of this piece of plant is 246 kilowatts. Or total output, sorry, should I say, it's 246 kilowatts. So that's a phenomenal amount of heat coming out of this device to heat the room. And so as a result, it's very, very effective at heating the church very, very quickly. The downside of consuming that much gas very quickly is the cost. So to run this piece of plant for 1 hour costs €52.50. So huge bill. And it reminded the church is doing this every single day. So very, very substantial. Those colder days where it's running it for a full hour, it gets very expensive for the church. Then we look at the air source heat pump, completely other end of the spectrum. What we found out is the heat pump, when it was using it, very rarely stayed at its rated output. It kind of cycled. It might turn off for 10 minutes every hour. We saw over the course of 4 hours, typically it would consume 30 kilowatts of electricity. So per hour, that's €1.79 per hour. So you're talking about this gas heater is consuming 52 euros per hour, and this air source heat pump is only producing or consuming €1.79 per hour. So massive difference. The obvious reason, or one of the main reasons why, is the actual quantity of heat coming out of the air source heat pump. So we're assuming a coefficient of performance of 3.5 for the air source heat pump. So it's only delivering around 26.5 or 26.25 kilowatts of energy to the space. Now that's very common in a retrofit solution. If you do it in your domestic setting, your air source heat pump is going to have a much lower rated output than your gas boiler. But it's just something to bear in mind here, because we're not heating the space over such a long period. It's only got to be heated for 1 hour a day. So vastly different pieces of plant there. To explain the reason why you would ever consider seating with an air source heat pump is the running costs or the heating performance. So what I'm showing on this graph here was the performance of the piece of plant. So if you were to put €1 of energy into each of these devices, how much heat would you get out? How many kilowatt hours of heat would each piece of plant give you? And you can see there the air source heat pump is returning about 3 times as much heat based on how much energy you provided. So the whole aim here will be to minimize the use of the gas heater, or eliminate it completely if we can, because it's way cheaper to use the air source heat pump. But being mindful as well, if the air source heat pump is going to need more time to heat up the space, suddenly fabric heat loss becomes a bigger part of the picture, and that's where it becomes really interesting. We'll drive on. So typically this is the way. This was a morning in March, not freezing cold, but typically this is how the heat pump operates. Heat pump comes on at 7 a.m. It's switched on. It runs until just before mass. most colder days, it doesn't get the mass up to temp, or the cathedral up to temperature. So then the air source heat pump might come on for 45 minutes and do the rest of the job. What we also see happening is as soon as that gas heater comes on, it's blowing really warm air in at about the same height as where the cassettes for the air source heat pump are. So the temperature probe on the output, or this is what we assume is happening because it happens every time as soon as the gas heater comes on, the temperature probe on the output of the air source heat pump goes, oh yeah, I've reached my set point, I turn off. So you don't ever have the two of them working together. As soon as the gas heater turns on, air source heat pump switches off, and then give it a couple of minutes afterwards, the temperature of the church gradually lowers and the air source heat pump just comes on to maintain temperature. So that's the way it is on a kind of a standard day, just to give you an idea of how it works. Hope that graph makes sense. It's 24 or 6 a.m. in the morning here until about lunchtime. So this is just a zoom in of the morning, and that's kilowatts consumption. So this is the actual consumption of the heat pump, and this is just the fan from the gas heater. So you know what I mean? So the actual electrical consumption of just the fan from the gas heater is greater than the actual consumption of the whole space heating from the air source heat pump. Here we go. What I'm bringing into now, the next step is to start looking at how all this actually affects the temperature within the church. So just to show you, that's the same thing we're seeing here. Air source heat pump comes on at 7 a.m. It's supplemented by gas heater. So we see here over the course of the night, this is our temperature probes. We have 2 probes just located at 2 different sides of the church. We can see here temperature dropping throughout the night as temperatures get colder. We have a tiny bit of solar gain happening here as the sun rises and it's getting a little bit warmer. Air source heat pump comes on around 7 o'clock. So we're starting off here at 13 or 13.5 degrees Celsius. Air source heat pump runs for 4 hours until about here, but it's only able to increase the temperature of the church up to about 14.5 degrees Celsius. And if people about to arrive in, it's not acceptable. So again, we have the gas heater comes on. You'll see how steeply the graph rises because of the amount of energy that this thing is dumping into the room. And yeah, you do just for the start of mass there, you get up to that 17 degrees, which is kind of what we're going to recommend as a kind of a standard day. Now, it's probably worth talking about now, and I've kind of mentioned it already, is like often case in a lot of buildings that we've worked on, when you have an air source heat pump, it's installed and it's let run. If you're dealing with a hotel or an office block or a domestic house, it's just left on and it's given a set point, and that's the optimal way. But in those deployments of air source heat pumps, you've usually taken a fabric first approach. So the fabric of the building is up to a very good standard where your thermal heat loss throughout the building is going to be minimal. Again, here, bear in mind that if we were to heat up this entire building, if we were to leave the air source heat pump on for 24 hours, which is what you normally do, it's our kind of expectation that it would still, in the colder days in winter, it would still struggle to reach that 17-degree set point just because of how poor the fabric is and how great the heat loss through the building would be at nighttime. And it would still cost the church about 50 euros per day. And you in a lot of instances, we expect you might still need to supplement with gas on colder days. So leaving it run for 24 hours just because of the nature of the building, we don't believe it is a kind of a suitable solution. One of the other big things we noticed, we really weren't expecting this, was when we looked at the temperature over time. We found that not only was the church, we were saying 17 degrees would be a good kind of goal for the church to have in terms of, what we should be aiming for inside there. Not only was it reaching it on most days, it was actually exceeding it. And some days you can see it here getting up to 20 degrees Celsius and 22 degrees Celsius. And the only time this was actually possible was when it was the gas heater was left on for maybe 10 or 15 minutes or maybe 30 minutes too long. Just to bear in mind the vast volume of air inside in this space, the amount of energy it takes to raise it by a couple of degrees is very substantial. So with our kind of operational recommendations, we'll be putting in kind of safeguards to hopefully that this won't happen again in the future, because it's very expensive to heat that volume of air up to 22 degrees Celsius. So what I've done here is I've actually just zoomed in on one of the days that it overheated, right? Just to give you an idea of, come on, usual story. Air source heat pump comes on in the morning, supplemented by gas heater. Gas heater runs, air source heat pump turns off. This stage, we're up to 20 degrees Celsius at both our temperature probes, so we'd be very confident that what we're recording is right. This turns off, you have a small drop, and then it settles around here. But the air source heat pump comes back on. So we're at 19 degrees Celsius, and the air source heat pump comes back on and tries to rise the temperature within the space. So what we think has happened here is that the set point has been changed on the unit. So this can often happen. We see this everywhere we go, is to be it an air conditioning unit and somebody it's far too warm. They keep pressing the button. They say set to 30 degrees, or they go as high as it'll go, and that can be left on for a couple of days. So that's what it looks like happened here, because if it was set to 17, there's no way it would continue to operate at, you know, its max output. And then to kind of compound the mistake, the gas heater comes on again, and we have further overheating of the space. This is, you know, very, very expensive and very hard to do. And, you know, up around 22 degrees, you're almost becoming uncomfortably warm. So what we've done is we looked at how the system performed at various start temperatures. So this is the temperature when, was it that 7 a.m. temperature? How able was the air source heat pump, or how close did the air source heat pump come to reaching that 17 degrees, and how much do we think we would need to supplement it with gas heating? So this is kind of our first cut at an optimized solution for the church. So what we're looking at doing is bringing back the air source heat pump to come on maybe 2 hours earlier, which would be very kind of upfront as well. When you're suddenly heating up the space, or when you're dumping in heat to a space now for about 6 hours, fabric heat loss is coming into the picture again. So we'll be very aware of that as we continue to monitor and kind of try and get this completely optimized over the next heating period. But this is our first kind of cut at it. We're saying on days where it's less than 12 degrees Celsius, you know, the air source heat pump comes on at 5. We suspect we're going to need that gas heater. We need to be, you know, very careful with not leaving it on too long, because, you know, every minute is about €1. So we got to just, you know, have a kind of rule, said, okay, we're going to leave it on for 45 minutes, and then the air source heat pump can come back on to kind of maintain temperature. And we have a sliding scale of recommendations. And we're kind of saying that if the starting temperature is 13 degrees Celsius or more, the air source heat pump should be capable of heating up that space. That's what we've seen. If it was given an extra 2 hours in the morning. So that's kind of our recommendation. And another very important one here as well is if the start temperature is 17 degrees or more, there's no need to apply any space heating to the room. I suppose an important point to bring up back in here is the users of the church and the guys in NC, they all have access to our platform, which includes the temperature and humidity sensor. So when they go into the mass in the morning to set up, they'll be able to see the current temperature inside in the space and make decisions off the back of that. It won't be them, you know, walking out and going off their own feelings to how warm or how cold the room is. They'll actually have a number to work it off, and they'll be able to make decisions off the back of that. So just to put in what we hope to happen off the back of these recommendations is, in total, we're hoping for a saving of about €3,500 if this goes to plan. Now, I actually haven't even taken into account the cost of overheating there. So I think this should be very much achievable. We'll be doing it, as I say, we did this piece of analysis from January to March of the year, just, you know, a few months ago. So by the time we did the analysis complete, we were into April, May, the heating season had passed us by. So this is very much for next winter as we move in. And as I say, if we find anything's not working or we can optimize it, we can come back and kind of try and hone it and come up with an optimal solution. And the beauty of having monitoring installed is you can see how your kind of suggestions are performing. So the last thing we're kind of keeping an eye on is, when I was looking at the performance, or when I was looking at optimizing the overall costs, we were looking at switching the customer over to a night saver tariff. Based on their consumption from January to March, only 14% of their energy was consumed at nighttime. So typically what we say is you want about 30% of your energy use to be happening during the night saver hours, which this time of year is it's at midnight to 8 a.m. You'd want 30% of your energy consumption happening then to justify switching over to night saver. At the time we were only at 14, so there's no way it would have made economic sense. But bearing in mind now, we weren't able, at the time we had no information on how the solar was performing. So if you have solar on a site, that's eating into your day consumption. So maybe we could see that 14 drift up slightly. That, coupled with the fact that I'm now requesting that the air source heat pump comes on an extra 2 hours earlier, that nighttime consumption is going to increase as well relatively. So that's something we're going to be keeping an eye on over the next few months. And yeah, so look, that's it. I'll open the floor to questions. I know a lot of people on this call might have spent more time working on historic buildings than we have. Typically, we work in more modern deployments with our monitoring solutions. So very interested to hear what questions you have or what suggestions you might have or any feedback at all. So thanks a million for your time, guys, and I'll open the floor there. let's stop sharing as well.
Thank you very much, Barry. That's excellent. We have a few questions there
Great.
on
I'll do my
the
best.
chat. Let's start at the top. What I would suggest is that the person that asked the question actually takes the question directly, so we get a bit more direct exchange. And I'd like to ask Simon Connolly or Caroline Akaboye, or both, to please take the first two questions.
Hello.
Good morning, thanks, or good afternoon. Thanks for a very interesting presentation. We think that the installation is a classic recipe for discomfort because it's blowing warm air above head level. And it's, sorry, can you hear us okay?
Yes, we can hear you fine.
We're just wondering whether you have the capacity to monitor mean radiant temperature, and in particular, if you have directional radiant temperature measurement devices, can you measure radiant asymmetry? Because this is probably the best indicator of comfort. You're putting an enormous amount of energy into the space in hot air, but you're actually not, the system, I know it's not your system, but the system is not really optimized for creating comfort.
This is a well. I'll take a bit of it. If anyone else from NCE wants to jump in, please do. So the question on our system is, like the way we built our system is we've developed the electrical energy monitor ourselves, but the platform we developed, practically any device that sits on Wi-Fi or Sigfox or Bluetooth or similar, we can integrate it into our system. So yeah, I understand completely what you're saying. You have a cold space and you're just blowing hot air. That's not a very comfortable thing to do. If there was an appetite for more detailed analysis, for sure we could embed more sophisticated sensors. What I'd love to hear, if anyone has worked in a similar, the challenge here is the short occupancy hours. And I'd love to see other technologies. One technology I'd love to see here that might fit what your frame of mind is maybe far infrared heaters that are often used in kind of like warehouses and places like that. So I'd be really interested to hear or to maybe measure how they might perform in this kind of deployment. And as you say, really measure the comfort. There's more to comfort than just temperature. So yeah, that's kind of where my thinking is, but we can of course embed additional sensors.
Okay, thank you.
Sweet, Barry, thank you. We do have another demonstrator on the project, and that's Tiggs Kirka in Umeå. And that, I think, tried to address some of these issues to do with comfort and radiant temperature. And I wonder if this will be an opportunity for Garish Nair from Umeå to actually comment at this point on the questions asked by Simon, and whether you had any success in looking at this issue of radiant temperature from the floor and so on. Garish, would you like to comment?
Yeah, the system in Cathedral is we have this floor heating. It is slightly different from the heating system in Core Cathedral. So it's a I would say there we have also monitored the various temperatures, including the radiant temperatures. So there we believe that with that system, because there we also tried with the possibility of intermittent heating, because in this texture can also the number of hours we need to heat the building is very less, few hours only we need to heat that building. It's highly underutilized. But it was found that it's not worthwhile to do the intermittent heating, because the benefit was very marginal if you do the intermittent heating. So it was decided to continue the 24/7 heating in that building. Of course, it is expensive, but still it was used because otherwise it was difficult to adjust the temperature. There the objective was to achieve the temperature about 20 degrees Celsius, 19 to 20 degrees Celsius, not 17 degrees Celsius. So it was difficult to achieve that comfort temperature within a few hours of time. So that's why it was decided to keep the number of like continuous heating, but possibility to reduce the temperature setting by about 16 degrees Celsius to the night time. and then keep the heating. So that could possibly, the cyclic heating could possibly save energy. That was one approach we suggest in the Tekshikan building. And that is one reflection I had.
That's great. Thank you, Garish. That's very useful compliment. Would you like to say anything on that, Barry, or should we move on to the next question?
No, I think that's perfect. I'd say we can move on.
One just to comment, like what this pew heating is, could be that a possibility in this type of church where you have the heating where the people sit. Would that be a possibility to have a better thermal comfort? And
if I'm understanding you correctly, you're on about an underfloor heating system where you radiate heat from the floor upwards. Is that correct? Is that what I'm catching?
No, that is one option. But apart from that, you could have like sort of a heating system connected to the where people sit.
Oh yes,
like
good point. Yeah, I know what you're saying. So you're on about only heat up the area that people are sitting in. That's your
especially if it is a very tall.
For sure. If you could even I'm not sure how practical that could be, but so there's two ways you could do that. You could either direct people to sit on one side of the church first, fill up over here first, and we're finally moving out of COVID, so that shouldn't be a trouble. And you directly reduce your heating consumption by a lot, and as well because of the cassettes, the way it's currently set up, you could easily do that with the control, so it wouldn't be very difficult. Again, it would just need buy-in from the priest in this instance to make sure that was okay. But definitely, yeah, actually it raises a good point that I never touched on, as well as the gas heater. I showed a photograph of it briefly, but all that heat is coming out of one side of the church. So that was one of the reasons we installed 2 temperature probes, just to make sure there wasn't a big temperature differential between the 2 sides. But it is kind of noticeable that one half of the church benefits more greatly from the gas heater. So potentially, if you were to try and only heat up sections that were, used by people, you'd have a direct reduction. Again, that would be kind of there's obviously a social element there to that as well, to make sure that the users are happy to do that, and the people that run it. But for sure, it would definitely have a direct reduction.
Great, thank you. The next question is from Kenny Eason.
I see that one.
Hey, so yeah, I was just curious, in the graph that you showed of sort of energy consumption with the heat pump and the gas warm air system sort of side by side, and I stress that I'm not an M&E engineer, so this may be a very daft question. Why is the heat pump sort of cycling in the mornings?
You're saying, why is it cycling even though it hasn't reached a set point? Why is it turning off for a couple of minutes?
Exactly, yeah.
I do not know the answer, and we've raised this as well. So a couple of things it could potentially be is, we thought initially, is there ice building up on the outside condenser? Is that what's happening? Probably not, because we looked at the temp. We thought that might have been at the start, but the strangest thing about this phenomenon, we haven't really understood it properly yet, is it happens sometimes, but not always, which is the hardest to kind of pin down to why is it happening. And initially we're like, oh yeah, maybe it's a defrost cycle happening on the heat pump, but you'd expect that to happen on the coldest of days, and it really wasn't. It's not happening all the time. The heat pump is switched off now, but it's an unknown, to be honest, Kenneth. We don't know. It's something we highlighted with them early on. We could see it. It was kind of evident to us. And the strangest part of that is it's happening sometimes, but not always. So there's a space there for the guys in the church to get onto the installers and see, is there a reason for this? But it's well noticed, first of all. And yeah, we haven't got to the bottom of it. And for sure, it's the main problem with that, outside of actual energy efficiency, is the whole challenge of the heat pump is it's weak at delivering a large volume of heat over a short space of time, and it's giving away further kilowatt hours of potential time to heat up the church when it's doing that cycling. So it is a noticeable problem for sure. Yeah.
Barry, is there a buffer tank in the system?
A buffer tank for what?
For the heating system,
for the heat pump. So once it reaches temperature, it switches off.
Mm-hmm.
Do you know if there is a buffer tank?
I'm not familiar. To be honest, I actually haven't been in this, ever even been down there to visit the site, so I'm not sure. I suppose my background is mainly electrical, and monitoring deployment wouldn't necessarily be in the design of heat pumps. So I'm not even too familiar when you say buffer
Sorry,
tank.
Caroline, what would the buffer tank be for, do you reckon? In that case?
The buffer tank is normally provided to minimize cycling, so that there's a big thermal inertia built into the heat pump system.
I think I understand what you're saying. Yeah, so you're saying it's inside and the working fluid is just given a buffer tank, so it's a more steady increases it, so it doesn't get that defrosting, is it?
That sounds like it, yeah.
Okay.
I expect it isn't there, but it's something that we can clarify with NCE perhaps, and come back with that to anybody who's interested. Indeed, we can put it on the website. I had a question regarding the what you mentioned about the night tariff, and this could be a bit naive, but did you think of the possibility of storage in combination with the night tariff? Because would it not be possible to store energy from the panels and actually get a cheaper sort of energy during the night and store it as well?
Interesting. Yeah, interesting. You're talking about energy arbitrage there. So you're buying energy when it's cheap and you consuming it when it's low. So the solar on site, first of all, since we've had the monitoring installed, maybe now on some of the holidays, it never exports. It's only 5 kVA, so it's small. The church almost never exports, right? So first of all, it's never worth storing that energy in a battery, because you can already use it directly. You need that energy on site immediately. So battery at the moment with the current size of PV only could be used for energy arbitrage, not for maximizing the use of renewable energy resources. You'd be doing energy arbitrage. Like in Ireland, you'd be making more now with the price of electricity. You'd be saving 20 cents a kilowatt hour, and you can only do that once a day, or about 20 cents per kilowatt hour, maybe even a little bit less, maybe 15 cents per kilowatt hour. You can only do that once a day. And you're maybe talking about installing a 10 kilowatt hour battery. It's a marginal kind of practice. I think battery, for sure, if you have a battery with solar, it can be a good technology to minimize export, and then on top of it, supplement or make further use of your existing battery by doing energy arbitrage. But the business case for energy arbitrage on its own, in most instances, with the way most sites use energy, is marginal. But again, here, like if you put more solar on the roof, that whole business case changes very quickly. So at the moment,
right, that's great. But I suppose you didn't really look at this as an option for the church.
Not directly. No, it wouldn't have been something that would have been directly on our radar.
Okay. The next question is from Kieran Smith regarding the heating profile of the church. Kieran, would you like to make the question directly?
This is it, yeah.
Hi there. It was, hi. It was more of just an observation than anything else. I found myself in a similar church in Glasgow several months back in Partick. And I've become a bit nerdy about things like this now, and looked around and saw the solution they'd provided for a similar sized large old church with an extremely high ceiling volume was to have directional infrared heating units dotted around the side walls. I suspect it didn't have I think they call it transepts, where you've got the extra bits beyond the pews to the left and right. So it was slightly narrower, but it meant that you had these heaters angled down towards the parishioners. And so it being infrared, it's transmitted directly, and it's a quick on and off. I have no affiliation to the church, nor do I have any contacts in it, but I thought to myself that that's a quick way to switch on and off, particularly for the common usage profile in many churches now. And someone beat me to it in the previous comment that you could theoretically offset that by looking at energy storage through tariffs. I'm not aware of the tariff rates in Ireland with regards to overnight off-peak, but I always think it looked like quite a good possibility for a property like this, but it would definitely require some sort of storage first.
That would be a possibility.
I'd love That's fantastic. I'd love to see if this church has, this is the one solution that like if you're looking at what they use, like, to be honest, this is less like a building and maybe a little bit more, you're not like, we kind of ignored fabric heat loss because we were heating for such a small period of time. We know the fabric is poor. We can't heat up for a long time. It's not a solution. Do you look at a direct, quick and comfortable heating solution? And I think far infrared could be a really good one, because you just reduce the amount of time that you're heating the space, and it falls directly on. Very easy to switch it on and off, as you've highlighted as well. So this is the one we've highlighted as, geez, this would be really interesting. If we could see data coming back on this could be a good solution for this church. And to be fair, like, relatively, I know there's other churches in Cork that don't have this, with relatively low cost far infrared. It's not a very intrusive. You mount it in the wall. It's relatively low cost. And then to add your point, the whole downside of infrared is it's you put in, it's, I say, very close to 100%. Is it in terms, you put in 1 kilowatt hour of energy, you get 1 kilowatt hour of energy out, or thereabouts, I'd imagine.
Yep.
Whereas with the air source heat pump, you're getting 1 in, 3.5 out. That's the benefit. So what you're saying here as well is, can you try and claw back some of that lost ground by storing energy overnight and deploying it during the day? So then the question is, how much infrared heat do I need to put out? Okay, infrared heaters are going to be on for an hour. What's the heat output for that hour? We'll say, is it going to be, I don't know, is it 20 or 30 or 40, or could it be 80 kilowatt hours? Then you kind of need to design your battery off the back of that, because you want to be able to provide most of that heat from that battery power and that. And it's a simple enough economic analysis. You're going to save whatever your difference between your day rate and your night rate is. You're going to save one of those cycles per day. How many years before the battery pays back? It's not the most complex in the world. If you're going to be you can only do this energy arbitrage once per day. How much does it save per cycle? And then just multiply it out over the lifetime of the battery and see, does it make sense? So not a very complicated piece of analysis to do on the battery, but very interested to see how well or how poorly, maybe, I don't know, the far infrared works, but definitely of other potential solutions that we'd have liked to have seen. I'd have far infrared at top of my list, just out of curiosity. It was one that came up early on.
Yep. Okay. Cool. I've remembered the name of the church now. It was St. Peter's, just as a period of reference. St. Peter's in Partick.
Glasgow.
But I don't have any contacts in it. I really just had to be at a service. Sorry about that. Thanks.
That's great. Thank you, Kieran. There's no other questions in the chat there, and we're getting close to our time of finalizing. But there's one question I'd like to throw in, just to create some concern about this. But there's a recent study that has shown that if Ireland's target of installing heat pumps in 300,000 homes were to be implemented, it would raise energy costs by around 46% because of the consumption that heat pumps would require. So it does look like, if unless we're prepared to put up with much higher energy costs, given the current cost of output, that heat pump solution is a bit tricky. Are you aware of this? Would you like to comment on this? And I suppose the issue is, are there no alternatives to heat pumps? And shouldn't really we be looking at alternatives that do not require such a high level of electricity consumption?
I think everyone could have their own opinion on this, call, but I suppose the only other solution that potentially is out there is biomass. Is that what you're hinting at, Jose? Is that kind of some solution that might be out there that would relieve because I suppose what's driving up energy costs or electricity costs in the case of heat pump, it's not just the heat pump, it's the fact that we're going to be looking at electrifying transport as well on top of that. So it's EV charging as well is going to drive up energy costs. Yeah, there's a huge kind of national kind of direction that we need to decide to go on. You'd imagine if we start to finally deploy offshore wind, you'd be hoping we could reduce our electrical energy costs and be less reliant on gas. I think 47% increase in gas now looks, who knows which direction that could go. So we might be facing energy increases across the board. So yeah, I think biomass is the only other one really that's out there, is it, that comes to my mind. that is a good solution. Now you need space to store the fuel, and if you're in a city centre environment, do you want to be, you know, the particulates or whatever coming off the back of it? How suitable is it? But sure, if you've got space and you're more rural and you're not so concerned about air quality, maybe biomass is one way to relieve the pressure that's on the electrical grid driven by heat pumps. So I'm sure there's lots of guys in the call that have other opinions that might differ from that in them. So I'd be interested to hear them as well.
That's great. Thanks, Mike. Thanks for that insight. So unless there's any final questions, I think we'll probably bring the webinar to an end. I'd like to thank you all for attending. This is one of a series of webinars related to the topics of Energy Pathfinder. We do intend to hold one or two more, so please watch this space. We intend to hold another one on co-design of energy improvements, and perhaps another one on an interesting project that we came across in Derry that has a similar profile to what we're looking at. Let me just check. I think there might have been another issue there from Kieran. Kieran, would you like to elaborate on the point that you make there?
Yeah, sorry. It's just really a food for thought concept. Looking holistically at how you would treat the hard to heat buildings within a common church campus. So certainly in Scotland you have the usual triumvirate of the church hall, the church itself, and the manse or ministerial residence. And so it might be worth considering in other projects looking at treating the heat load of the whole, and the obviously the switch on, switch off ability of using heating in one building and then switching it off again could be a consideration as well. Use profiles then become more important, because you could, wherever possible, you could recommend to the church that many of the functions that we do and serving the community could be done maybe in the more modern, easier to treat church hall compared to often cases the much larger, hard to treat historical building that the church is. And so treating it as a whole, you might actually find an overall efficiency for the one customer being the church.
Yeah, thank you. I think it's been generally demonstrated that district heating arrangements can be more efficient than individual ones, and that actually being limited to one building does not produce the most effective systems. And certainly some move towards district heating would be a good strategy. Thanks for that. So please keep an eye on our website and make sure that you're on our mailing list for future webinars. Your comments on any points made, any questions that might arise afterwards are welcome. Please email them to us. Again, you have our email address there through the website. And once again, thanks to our speaker, Barry, for a very interesting presentation. Nice to see the positive work that is being done by NC Insulation and yourselves regarding the core cathedral for the benefit of the project. And thank you. I look forward to meeting all of you again at some stage. Thanks for attending.